All right, welcome to lesson 4. Here we're going to be adding and subtracting rational expressions. Keep in mind that we're working on performing operations like multiplication, division, addition, and subtraction, not just to be able to do them, but because when we're working with rational functions that reflect real-life situations, we need to be able to do these things fluidly and easily to make more sense and to solve rational equations. Okay, so go ahead and complete these addition and subtraction problems, and then use those to write a rule for adding and subtracting fractions with a common denominator and for when there are different denominators. Alright, so the ones with common denominators, A and B, are quite easy. If I have 3/10 of something and I have 6/10 of something and I add them together, I now am going to have 9/10. And similarly, if I have 5/7 and I subtract away 3 of those sevenths, clearly all I am left with are 2/7. So to make this much clearer, I am taking the numerators, performing the given operation of subtraction, and the denominator that is common remains. So I'm left with only 2/7. All right. The problem that we run into with C and D is that the denominators are different. And to clearly illustrate this, we could draw a picture of 2/5 and a picture of 1/3 and see what happens when we try and add them together. So to do that, consider a number line. So we'll have two number lines. The first one will represent 2/5. Now 2/5 is less than 1, so I think of 2/5 as being 2/5 of 1. So here's 1. And to find 2/5, what I'm going to do is I'm going to split this up into 5 equal parts and highlight 2 of them. So here I've split up my 1 unit line segment into 5 equal parts. Notice I'm between 0 and 1, 2/5 between 0 and 1. And now I'm going to highlight 2/5 of them. All right, so there's 2/5 represented, and now I'm going to represent 1/3. So what you should do is actually represent it on your own the same way that I've represented 2/5, and think about adding those two line segments together and seeing what would happen. Okay, so here is 1 unit line segment again, and I'm going to highlight 1/3 of it. Now, I'm going to add these line segments together because that's the result of the sum of these two fractions. So notice what will happen if I take this line segment here and I add it on to the end of this one. What's going to happen? What you'll notice, I think, is pretty clearly, right, if I add on 1/3, the length of this line segment is going to get me to about here. And that is unfortunate because I can't tell exactly what that fraction is. But let's go ahead and do that so that we can see that this is really the case. Alright, so what I have done is I have taken 1/3 and I've added it to the end of 2/5. In other words, this line segment, the blue and the red together represent this sum. Can you tell me the length of this sum? You can't. You don't know exactly how many fifths it is. You could approximate it. You know it's in between 3/5 and 4/5, but we need a specific answer. Similarly, you can't tell the exact length of this line segment in terms of thirds. If you took this line segment and matched up along the thirds, you'd get a little more than 2/3, but you don't know specifically what it is. And if you think for a second about what we'd have to do so that when we added these line segments together, we'd know exactly the value, we will need to write 2/5 and 1/3 both in terms of the same number of segments, so that when we then add them together, we'll be right on a segment line and we'll know exactly the value. So the question, of course, is how do we do this? And looking at it geometrically, at these line segments, it's pretty obvious. We need to find a number of segments that we can split both the 5-segment line and the 3-segment line into. In other words, we need to find a number that both 5 and 3 go into. So thinking about this, you can imagine 15. I can take this fifths line and turn it into 15ths by taking each of these 1/5 and splitting it into 3 segments. And I can do the same for this thirds line by splitting each of the thirds into 5 pieces. So I'll have 5 times 3, 15 pieces, and 3 times 5, 15 pieces in each segment. Then when I line these up, I'll have an exact number of segments because this blue line and this red line will be measured in common terms, in 15ths. And so when I add them together, it'll make just as much sense as the first two. So with fraction work, of course, I want to create an equivalent fraction, so something that's worth the same amount, but is in terms of, instead of fifths and thirds, 15ths. And so, of course, to do that, I need to change these into 15ths. The way I do that is multiplying by 3 over 3 and by 5 over 5, so that I don't change the value of each of these fractions. I'm multiplying by a form of 1. I get 6 15ths plus 5 15ths, and of course, that makes sense. It should be 11 15ths. And I have no trouble saying that is precisely the answer. All right, so use the same reasoning to go through part D here. And assuming what you did is you said, okay, I need a common denominator, so I need to find a way to make both denominators look the same. And what you probably did is you went and you said, okay, let's multiply this by 15 over 15, and this by 20 over 20. And if you do so, you will end up with negative 35 300ths. So using these examples, you construct a rule, and the rule should go something like this, and you might have written it out in symbols or variables or whatever it is. When you have a common denominator, you simply add the two numerators and keep the denominator the same. Very simple. But when you have non-common denominators, you need to create a common denominator. And if you look at the strategy that we've used, we've multiplied, so for example, taking a look at 20ths and 15ths, we multiplied 20 by 15 and 15 by 20, and then did the same with each numerator. And that guarantees that we'll have a common denominator. However, what you might notice is that when we get our result, it's not that pretty. This is a kind of nasty fraction, and you can tell just by looking at these two values that you can simplify this. Both of these values are divisible by 5. And what that means is that we actually didn't do a very good job of coming up with a common denominator. In fact, there was a much easier common denominator that was much smaller than 300. And if you think about it, and you look at 20 and you say, okay, the multiples of 20 are 40, 60, 80, and then you think about 15, and it goes 30, 45, 60, and you realize that 60 is a common denominator that we could use, which is much smaller. And the way that we can see this is by writing out 20 and 15 in factored form, just like we'll do with rational expressions. So write out 20 and 15 in factored form, and when I say factored form, I mean write them in terms of numbers that are prime numbers that multiply together to give you 20 and multiply together to give you 15. Alright, so I've done so, and notice I wrote 20 as 2 times 10, but I said prime numbers, and so this will help you see where the other two prime numbers come from. 10 is 2 times 5 again. So what I have is 2 times 2 times 5. That'll give you 20, and here I have 3 times 5. Now, notice how much easier it is to see what I need to do to this denominator and this denominator so that they're the same. Because they have a 5 in common, I'm not going to need to multiply by 5 over 5 on either of my fractions. To make these two look the same, all I need to do is multiply by 3 here and by 2 times 2 here, and I'll end up with a common denominator. Alright, so now when I do this, notice that my denominator here will be 2 times 2 times 3 times 5, and here I'll have 2 times 2 times 3 times 5. And of course, both of those are equal to 60, and so now I'll have a common denominator of 60. And 60 is the least common multiple of 15 and 20. It's the smallest number that both 15 and 20 go into evenly. So it's going to be the best choice for a common denominator. In fact, you'll find that if you use this common denominator of 60, you're going to get an answer that is simplified already. So notice that I can simplify negative 35 300ths. I can divide both by 5. Not surprisingly, and I will get negative 7 60ths. But if I simply choose a common denominator of 60, when I do the subtraction, I'll end up with negative 7 60ths and won't have to simplify. So this is what we're going to want to do when we're adding and subtracting rational expressions. All right, so here's the protocol for adding and subtracting rational expressions. Go ahead and pause the video quickly and write down the steps here. I'm going to leave a little blank space over here so that I can go through an example, so you might want to do the same. All right, so let's quickly go through this. We follow the same procedure as when we're adding and subtracting rational numbers, i.e. fractions. First, we want to find a denominator that is a common multiple of the other denominators I'm dealing with, right? A common denominator. But we want it to be a multiple that is as small as possible, the least common multiple. And then we're going to rewrite each expression as an equivalent rational expression, meaning that I'm going to multiply both the numerator and denominator by the same value so that it's still equivalent to the original fractions or rational expressions that I had, but so that there is this new common denominator that will allow me to then add them together. And then I'm going to apply the rule for adding or subtracting with the same denominator, right? And this rule is very, very simple, right? If I have A over B plus C over B, because it's a common denominator, I can simply do A plus C over that common denominator B. And the same works if I am doing subtraction. All right, and of course, the only thing that would make this run into trouble is if B were 0, so B can't be 0. All right, let's do a quick example and then get on to some practice. Okay, here's the example that we're going to do. Go ahead and try this first on your own, following the steps. Don't take too much time. You should be able to get it, and then we'll take a look at it together. Okay, so there's not a lot of factoring that we need to do here, but there is something that I can notice. What I would like to notice is that 3x and 5x squared differ in that one has 3, one has 5, and this has x, and this has x squared. So if I write x squared as x times x, I think that'll make it a little bit easier to see. So I'm going to do that just for the purposes of this example. Now, I can clearly see the ways in which the two denominators differ. While both of them have an x, in order to make them the same, I need to multiply this by 5x, so that I'll have 5 times 3 times x. And I'll need to multiply this here by 3, so that I'll have 3 times 5 times x times x. In other words, I'm seeing what the two have in common, and then I'm taking whatever they need that's left over that they don't have in common, and I'm using that to multiply to make my equivalent denominator. So it's helpful to find this denominator and write what that denominator is going to be off to the side, just to make sure. So I know that I'm going to have 5 times x times 3, and that's going to give me 15x squared, which I can see just by looking at my original situation. All right, so that's analogous to step 1, and I want to put just a little hint. Make sure you factor. Now, of course, I'm going to multiply both of my rational expressions by the necessary fraction so that I get a common denominator, and that's, of course, going to be step 2. All right, now having done that, I can apply the rule for adding fractions with a common denominator. In this case, I'm subtracting. And so I will end up with 20x minus 9 over 15x squared. And notice, because I took the time to provide the least common multiple, the best common denominator, I won't have to do any simplification at the end. And if I'm looking at the domain here, I can clearly see that what will make the denominator 0 is when x is 0. So my domain would be all real numbers except for x equals 0. And I'm done. Okay, so let's take a look at a couple of more. Try these first on your own quickly, and then we'll go over them in very short form and give you 2 more to practice on your own. All right, number 1 is nice and easy, and the reason that is that 4 is 2 times 2, and 5 is 5 times 1. So we know they don't have any thing in common, any factors in common. So the least common multiple of 4 and 5 is 20, and so we'll have to multiply by 5 over 5 and 4 over 4. All right, and now I have a nice common denominator. Notice that I have to multiply the whole numerator by 5 here and by 4 here. So I'm putting parentheses around just to remind myself that I need to distribute. Now that I've distributed, I can add them. And doing so, I end up with this in the numerator. Notice I've put parentheses here, and this is to remind me that if this were subtraction, I would need to distribute the negative sign in, but this is addition, so it won't be changing the sign of each of these values. So I can go ahead and collect the like terms. I'll have 5a plus 8a be 13a, and 5b minus 4b, which will be 1b, all over 20. All right, there's the solution to number 1. Notice, of course, that the domain here for this particular rational expression is all real numbers because the denominator will never be 0. All right, go ahead and try number 2 again on your own, and we'll take a look together. Okay, glancing at number 2, I notice, of course, that both the denominators are polynomials, and so factoring is going to be critical here. I want to come up with a common denominator, but I want to make sure that it's the simplest one possible. So I'm going to need to factor both denominators, see which factors, if any, they have in common, and then make sure I multiply by the appropriate values so that I end up with a common denominator. So go ahead and factor if you haven't already, and see what you'll need to do to write equivalent expressions with a common denominator. After factoring the denominator, I notice that the factor that each denominator has in common is x plus 1. So for this denominator, I'll need to all of a sudden multiply by 2x, and for this denominator, I'll need to multiply by an x minus 4. So just to make sure I'm clear, my common denominator is going to be 2x times x minus 4 times x plus 1. That's going to be my full common denominator. And after multiplying to create equivalent rational expressions, I'm adding. So notice I've kind of done 2 steps in one here. I multiplied 3 times x minus 4 and got 3x minus 12. And here 5 times 2x will give me 10x. So because I'll have a common denominator, I can add the numerators together. And my common denominator is going to be 2x times x minus 4 times x plus 1. That's what I'll have on both denominators. And so that's my new common denominator. Adding some like terms in the numerator to simplify will give me 13x minus 12 over 2x times x minus 4 times x plus 1. And there is my completed answer. Notice that I've left my denominator in factored form. And to show you why I did, I want you to quickly figure out the domain of this expression. Hopefully you realized to figure out the domain, I need to find where the function is undefined and then say that it's defined everywhere else, or that's what its domain is. And since this is in factored form, setting the denominator equal to 0 can be done in my head. With all the work we've done with polynomials, we know that this will be equal to 0 when x is equal to 2, when x is equal to 4, and when x is equal to negative 1. So my domain will be all real numbers except 0, 4, and negative 1. All right, I'm going to give you 2 more to practice. Be ready to present them tomorrow. All right, here are the 2 more for you to try. Make sure that they are fully simplified when you're complete, and go ahead and write down the domain for each of the final expressions.